One is that they're simple, pretty simple and memorable, and the other is useful. So I hope you like it, and nothing too complicated to get through today. Also, a lot of fun besides, I hope. So now the main thing that I'm addressing today is, what do you do if you have lots and lots of disks? It used to be when I started learning programming, we got a kind of a jukebox thing, which was called a disk, a BRAMAC, at our computer center during my senior year, and this was a great, huge thing which would go chug, 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 and I think I broke the arm, actually. The first program I wrote for it, I found I implemented integer programming. Ralph Gomer had just invented a new integer programming algorithm, and I implemented it. He told me later he thought it was the first implementation of it, but unfortunately we found out it would have probably taken about 20 years to do the thing. We didn't have very much computer memory in those days, and this disk was huge. It probably had half a megabyte. And I saw, when I visited the Soviet Union in the 70s, I saw their disk unit, which had to be kept in a separate room. The disks were really huge, massive things, even more massive than the one that's out on the first floor of Gates here, which that Libroscope disk weighed how many tons, I don't know, and so these were really massive things. And when we talked about mass memory in those days, it was not only massive in size, but in mass storage. It was massive in weight and it also had supposedly a lot of bits on it. Well, now, however, since the late 80s and the early 90s, the things have not only gotten smaller and smaller and smaller, but they have more and more things on them. I read a couple of weeks ago that IBM announced another order of magnitude in density that they're going to have in their products in a couple of years, and it's also cheaper. So now we can, now it's not too uncommon to be thinking of 5, 10, 50, maybe even several hundred disks in a disk farm, which used to be only at Fort Meade or someplace where they had that many disks. Now, we need new algorithms for this phenomenon, and pretty soon it'll be true that people will have their own chance to use these. Even people on our desktop will probably have a situation where we have multiple disks, and so I wanted to show you two things. The first one I'm going to talk about is for when you have two disks. And the next one is, not two disks, two-way merging on any number of disks. And then the next one is where we're going to do K-way merging, or large-scale merging on lots of disks. Now, the easiest way to handle lots of disks is something, I don't know who first invented this term, but it came out in the late 80s. It's called disk striping. How many people know what disk striping is? Just curiosity. About half of you? No, a third? Okay, so disk striping, and this is just a nice buzzword, but it's also a nice idea, and it means that you take and I like to actually now subcategorize it. So the simplest thing, which is not one of the two I'm going to mention, is the idea of superblock striping. And what it means is this: if I have several disks, well, what should I don't even want to have to draw them as here. You want to see an illustration from Volume 3? Here it is. This is the new edition of Volume 3, my book on searching and sorting, which should come out in a couple of months, and I still got 100 pages to write, but it's next, 2 more weeks and I'll be ready to work on the index. Now this is, and this stuff I'm talking about is from the new section about disks. So anyway, but suppose we have lots of disks, and what we do is we imagine that we have to to write blocks on a disk, A0, A1, A2, A3, A4. These are the blocks from file A, and we have to put them on the disk. But maybe we got 3 disks, and so what we do is we put A0, A3, A6, A9, and so on the first disk. We call it disk 0, actually the 0th disk, and then the disk number 1 we can put these guys, and disk number 2 we do this. And so now, and this is, and we also range it so that, so this is disk 0, disk 1. We arrange it so that these are in the same place on the disks too. So in the same track, the same cylinder, so that whenever we have to do some head motion, it's the same on all of them. Well, then we just consider A0, A1, and A2 to be superblocks. The actual A0 might be one track full, one revolution of the disk, for example. But basically, it's really one buffer full of information that we would input or output at one time. We give one command, and it says fill this buffer with this block, and that's what a block is here. And we consider that, and we consider A0, A1, and A2 as if there was one super block. And then whenever we want to read in, instead of reading in one block at a time, we read in 3 blocks at a time, one from each disk. And so it's just as if it was a super block of 3 times the size. And so if you have D disks and B items in a buffer, then in fact the super block has DB items in its buffers, and so we're just increasing the size of our buffers by D, but we're also speeding up the I/O operation by a factor of D, because we can do the 3 reads simultaneously. Okay, so that's very simple, and this arrangement of the stuff on the disk is called striping the file, and that basically all we have to do is consider that we use the same old algorithms we had ages ago, but now we gain a factor of D in speed by if we're willing to give up a factor of D in our memory. Well, we have a lot of RAM too these days, but there are better algorithms by which we can get the same speed for less RAM, and then therefore we can make we can maybe read larger amounts of stuff with one I/O command and not have to worry about seek and things like this. So the idea of the new algorithms is to try to do better than superblock striping, and the first thing I want to show you is the way we can get a factor of 2 with a really neat idea that was known to magicians, but as far as I know had never been applied before in the real world. But I'm willing to be told differently. So we gain a factor of 2, meaning that without having to buy extra RAM, you can do twice. You can do as well as you could have done with twice as much RAM with this, as far as your disk I/O is concerned. And this applies to a general problem which occurs when we have 2 files that were merging together. So we have not only A0, A1, A2, A3 blocks that we want to process. This is in one file, but then we also have another file, B0, B1, B2, B3, and we're trying to do something that looks for corresponding keys in the 2 files. So the 2 files are in order by some kind of a key. Now, sorting is one example of this, where we're doing a 2-way merge, but there's lots of other cases. For example, we might be doing a join of two relations. We might have 2 queries, and we want to take the AND of them. So you're looking up something in the library, and you say what. You give the author's name, and so you have a big list of all the things by that author. and then you have another thing you give a title, and then you want to find out the intersection of the records by that author with a certain title. And for large, complicated queries that we might be doing with Alta Vista or something like that, we have huge files that we have to that we want to bring together two files in order. Many data processing applications have a master file and a transaction file where we want to match one file to another. So lots of cases exist where we have two such files and we want to do fast I/O on these files. Now, before I give you the method, I want to show you the trick. So this morning I bought a pack of cards. Did you know you can get cards that have Stanford? Look at this. Can you zoom up on that? Isn't that beautiful? So you got cards that have Stanford University on them, and I'm going to show you this trick. And the people in the audience before the lecture here chose someone who was going to help me with the trick. Your name was Hovalv, is that right? Okay, so let me show you the trick, and be sure we get it on camera here. I'm just going to deal out a bunch of cards here. Can you see it on the screen up there? Yeah. Okay. Good. Okay. What?
Good shuffling.
Oh, well, I should have cut them actually, but I forgot. I'm too nervous. Now, okay. Now, hold on. Give me a number between 1 and 10.
4.
4. Okay. So I give D4. Okay. Now you'll notice that this. I had no idea how many he was going to say. Okay. Now Bruce wants me to shuffle them, so I'm going to shuffle. Okay. So I'm just going to shuffle them this way. All right. This is part of the trick, of course. And watch the shuffle. Uh-oh. Problem. Okay. Here we go. I never have done this before, so let's hope it works. Now, here's what I want to show you. I'm going to deal out the top 4 cards. Look at them. You notice there's 1 diamond, 1 spade, 1 heart, 1 club. All right? Okay. Next 4. 1 of each. I shuffle them. Okay. All right. Now this is called the Gilbreth principle. It's invented by a guy named Norman Gilbreth, who was he invented the case of 2 suited of just red and black. It also works for just 2 at a time. I'll get 1 red and 1 blue, one black. Okay. But if I take them 4 at a time, I'm getting 1 of each. Okay. And the Gilbreth he generalized it to n cases, and in this case we think of it as the number of disks we have is the number of suits, and so this would correspond to 4. Maybe if I had 4 disks and I wanted to if I knew what the next 4 things I wanted to read was, I could issue 4 disk commands simultaneously if they were all at different disks. If there's no conflict between the reads, sure, no conflict. But if I had to read from two from the diamond disk, that would take longer. Okay. All right. So he generalized this principle sometime in the 60s, and I talked to him on the phone. He worked at Rand Corporation at the time, and never published anything except finally in a magic journal. And he says that actually this Gilbreth, it's called the Gilbreth principle now, has been the subject of more than 100 magic tricks in the magician's literature, and there's a book coming out in French this year about the Gilbreth principle and so on. Now, it's not really magic; it's mathematics. Although some people think that there's a connection, and I'll explain to you first the trick. As you might have imagined, it wouldn't work if I kept shuffling the cards, but I shuffled them once. All right. So here's another deck, and the first secret that you have to know is you have to take out the jokers. Okay, but then my original deck, I just had the cards in indefinite order. In this case, let's say diamonds, clubs, hearts, spades, diamonds, clubs, hearts, diamonds, clubs, hearts, spades, diamonds, clubs, hearts, spades. That has to be the sequence that you go diamonds, clubs, all the way through the same order. Okay. Then when I started dealing the cards down this way, it doesn't really matter what number you said. I could have stopped after 1 or whatever. But what's happening is that after I've got to the point where I'm starting to shuffle them, I've got them, instead of calling diamonds, clubs, hearts, spades, let me imagine that I had 5 suits. And I started out 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. This would be for a 5-suit deck. Then I would have dealt some off the top. And so after I've done the first part of it, they're going to be sitting there 4, 3, 2, 1, 0, 4, 3, 2, 1, 0, 4, 3, 2, 1, 0 until we get to the end of that deck. So after I've dealt off something that's 0, 1, 2, 3, 4, 0, 1, 2, 0, 1, 2, 3, it's going to be, well, it might not be, it might have started, it's what's actually happened. I dealt off a 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, and 0, 1, 2, and then I've put on I've put my 3, let's see, does this Gilbert's principle really work? It's not. Seems to work. Okay, so let's see, if I've got them, so I just put the 2 on the, this is the order in which I dealt cards off onto the table. And so on the table, I had a 0 on the bottom, a 1, and then a 2, and a 3, and a 4, and so on. I ended with a 2. And so at the bottom of the deck on the table is a 0. At the bottom of the deck in my hand is a 4. 4, 3, 2, 1, 0. And so after I shuffled them, I got the cards at the bottom of the deck were shuffled. I took a few from this, and then I took a few from here, and then I took a few from here, and a few from here. And the kind of shuffle that I did is just called a riffle shuffle, which takes any number from the left and any number from the right, and then go back to the left and back to the right again. But all of these cards stay in the order that they were in, and these stay in the order that they were in. Okay. Now, so if we look at the first 5 cards that I get out after this shuffling process, there's going to be K of them from this side and 5 minus K from this side. So the K might be 0, 1, 2, and this might be 4 and 3. But you notice that it's 1 of each. Now I'm poised, now let's suppose I get 2 from in the next round, maybe I get 1 from the left and 4 from the other one. So that'll be a 3 from here, but this will be the 2, 1, 0, 4 from the right. Okay? In the next one, there might be, 2 from the left, 3 from the right. So that would be the 4 and the 0 from here, and the 3, 2, 1 from the right. Okay? You with me? No matter what happens after the shuffling process, this thing is still enough in order that I'm always going to get I'm always going to get the 5 suits in some way. So that's the Gilbreath principle. Now we're going to apply that to this disk striping idea, and so we got we got our file A0, A1, A2, A3, A4, which I'm striping actually on the disks. So I'm putting A0 here, A1, A2, A3, A4, just like I said before. This is 5 disks this time instead of 3, but I stripe the B's on the same disks. I stripe B4 here, B3, B2, B1, B0. So B4 then B9 will go this way. So the B's are striped in the reverse order. So disk 0 to disk 4, but the B starts at disk 4 and goes the other way. 8, 7, 6, 5, and so on. This would be B10, B11. Okay, now when I'm doing the merging process, I need a small auxiliary file that's going to tell me how to prefetch. It's going to tell me which 5 blocks I'm going to need first. Now, this is the only slightly tricky thing that you have to keep in mind, and I'm going to say alpha 0 is the key of the last record in A0. So A0 contains B records. You know, it might contain 100 records, 1,000 records, but and they all have keys, and the keys are all in order. I look at the very last key in that block, and I'll call it alpha 0. And alpha 1 will be the last block in A1, and so on. And same with the betas. This is an old trick called forecasting that was used in tape sorting on the first UNIVAC way back in 1949, 1950 by Betty Holberton invented this. So now by looking at alpha 0 and beta 0, these are the last keys in those first two blocks. If alpha 0 is less than beta 0, then I'm going to need to see block A1 before I need to see block B1. Because you can imagine how I'm actually merging all. Suppose I was doing this by a simple-minded method where I just put A0 into one buffer, B0 into another buffer, and I started matching records. And if you found two keys that were equal, okay, you merge them, great. If one has a smaller key than the other, then move ahead in that file until you get to two matching keys, or if you're merging output the smaller key, whatever. The idea is to go through and then when you get to the end of the buffer, then you have to read again. The buffer that's going to empty first is the one that has the smaller last key. So by looking at these last keys, which I'm assuming now are going to be stored in a separate file somewhere, and this is order of magnitude less information, much less information. So we can assume that when these files were prepared, this extra information was written out by the operating system for us. So by looking at these keys, I will be able to determine the sequence in which I'm really going to need those blocks. It might be A0 and B0 I'm going to need first. But then it might be that I need A1, then I maybe A2, then B1, and then A3, A4, B2. Now the B's are going to start catching up, B4, B5, B6. I'll need A6, B7, B8, A7. You get the idea. There will be some order like this. But this is just like shuffling two parts of the deck together, where the A's was what I had in my left hand, the B's was what I had in the right hand. And so if you look at the first 5 reads here, that I want to do, I can start issue all these 5 reads simultaneously, because look at A0, B0, A1, A2, B1. These are on 5 different disks. So, whammo. I can do all these reads simultaneously, no conflict. Same for the next 5. That's Gilbert's principle. It's exactly the same as the card trick so either you guys can use this if you have a deck of cards and you want to show your friends, or you can use it if you have a bunch of disks and you have to have some process that merges two files together. But basically, if you count how much space you needed compared to the Superblock strategy, you saved a factor of 2 in this thing. Any questions on this? Come on, ask a question. Huh? It's not questionable at all, right? So one of the things Norman told me on the phone was that people ask him what to do if his principle doesn't work. And they still think it only works most of the time. But it doesn't. It works absolutely all the time, unless you goofed and one of the disks is down or you left a joker in or something. Yeah, the question back there, Jan?
Is it generalized to K? So A, B?
No. So unfortunately, this only works for 2 input files. It works for any number of disks. So the number of disks doesn't matter. D disks for any D. So one of the amusing things with the Gilbert's principle is that you take two decks of cards that are, one is in order from like ace of clubs down to king of spades or something, and the other one is in absolutely the other order. And you shuffle them together, and you look at the top 52 cards, and you get a perfect deck. And the other one is a perfect deck too. Okay. So the Gilbert's principle works for any number of suits, or including 52 or something like that. oh, by the way, hold on, I give you a souvenir. It turned out that there was an extra ace of diamonds in there.
What kind of quality control is that? What kind of quality control is that?
By the way, these Stanford cards are made in Hong Kong.
Do you have an algorithm for writing the B's backwards on the disk?
No. The B's have been, when they were striped to the disk, you made sure that one of the files was striped in the other order. So you had to do this. So you had to prepare this, by looking ahead.
So you need a buffer at least to do it.
No, I think I would have always written my. When I'm in my application, which is deciding how to do the two-way merge. It gets its data from somewhere, but the data didn't come. Unless somebody shipped me the disks. You can either you have to. This data was built on the fly by somebody. Yeah, it has to get there somehow. The data was generated by some process, and that process wrote out the Alphason data and also did this reverse striping. Yeah. But that's a good point. But I have a feeling that this might apply to other to other things now besides merging, where you want to gain absolute parallelism, that people can you've got sort of a positive and negative worlds, and you can make sure you can save a factor of 2 for part of your action anyway. It's something like this trick that we had for having a stack grow from the bottom of memory and from the top of memory and grow together. There's a trick, you don't have, you can allocate memory from the bottom and from the top, and then you don't know which of the 2 lists is going to be bigger, but they can share the same memory, and that doesn't generalize to 3 lists, but it does for 2. And so anyway, but this is the trade-offs on it. And you never gain more than a factor of 2 by this technique. It doesn't gain you a factor of D, unfortunately, but it's still I think kind of cute. Question?
It seems to me that the heads are flying around on the disk pretty wildly. I mean, if you go on disk 1, you need an A and then a B and then an A again. The head goes back and forth.
No. We also have to work out that that these are on the same cylinder.
Oh.
Yeah. You have to. Yeah. So we'll have to take a chance that the B's don't get too far ahead. That's right. Yeah, because they're on the same disk, but yeah, we want to try to keep them close by. That's another factor, right?
I don't think it matters because there are different disks, so you have different.
It matters if you have control over the if you're a standalone if the operating system usually protects us from these little being able to control this, but I think in the future we'll have a chance to actually not have to take a random disk seek every time we do a disk access.
Most RAID systems normally are, for them it's from the user's point of view it's irrelevant in what.
Yeah, I know, the people who are winning these sort competitions in the Sigmod races have to have control of their disks in order to do it. And I think anyway we like to have these. We'd like to have full track reading and things like that in order to avoid the latency time. But we also like to have some way of minimizing the seek time, and if it's hopeless to minimize the seek time, then you don't have to worry about this detail. That's true. Okay, now let me get to the next technique, which I want to call randomized striping. And how are we doing on time? Okay, good. Randomized striping. In this case, this is what I recommend for large order of merge on a large number of disks. It's again a fairly simple idea, but I want to I want to introduce it by slowly, so I'll give you an example out of the book here. And let's suppose that in this example I'm doing 8-way merging. Well, I got she can focus up on this pattern here. I have 8 files to merge, and they're called A, B, C, D, E, F, and G. And one of the orders in which we might need to process the files might be this. A0, B0, C0, D0, F, G. We first have to read the first block of every file, then maybe the D is going to exhaust first. So we need D1, then E1, and D2, E2, D3, A1, and so on. And again, by just looking at the last keys in each block, we can tell what this order is. Now this order we call the chronological order of the file, and we assume that our software is able to figure out the chronological order. This is this small extra information about the last keys gives an entire information about prefetching as to which blocks are going to be needed in which order. And in the rest of my discussion, I'm going to assume that we know the future as to what order we're going to have. Now, in this case, I've striked the blocks. For example, AJ goes on to disk J, modulo D. So, but BJ I'm putting on disk J plus 1 mod D. So the B0 is going to go on disk 1 and C0 on disk 2, and that way. So now let me write these files in chronological order, but on the disk that they are. So I'll make a disk 0, disk 1, 2, 3, 4. A0 is going to be here, B0 here. Chronological order. I'll move to the right a little bit. F0 is here, G0 here, H0 is here. Now, the next one I need is D1, then that is sitting down here on disk 4. Then I need E1, which is up here, D2, excuse me, still getting over this cold. D2 is sitting here, E2 is sitting here, D3 up here, whoops, no, D3 is here, A1, where's A1 is going to be on this disk, F1, oops, that's on the same disk, B1, that's over here, G1, same as B1, A2 is going to be on this disk, F2, this disk. You can see where F1 was, so I know where F2 was. E3, E2 was there, so E3 is also here. D4, D4 is on this disk too. I'm getting a lot of congestion on disk number 2. C1, same disk. H1, this is not a random example, eh? H1 is down here. C1 is down here too, good. Okay, glad you're watching. I wish I had done that intentionally, but I did. B2 is down here, G2 down here, A3, okay, F3, E4, D5, okay, those are all sitting on disk 3, and D6 is down here. Okay, now, let's suppose that I had infinite buffer space in my machine, and that the only resource was that I had, so I want to minimize the disk time. So at time 0, I will read, at every time I'll read from every disk. So at time 0, I'll be reading A0, B0, C0, D0, E0. And at time 1, I'm going to read F0, G0, H0, C1, and D1. See, I'll know that I can look ahead, so I can see that C1 is the guy I'm going to need before on disk 3 before I need H1, for example. At time 2, I will read the third guy from every disk. So the third guy on 0, third guy here is E2, third guy here is B1, the third guy here is H1, and the third guy here is D6. Okay, so I'm reading D6, before I'm reading D2, because it happens to.
Because it's free.
because it's free. Because D2 is, yeah, okay. So that's the idea. This would be the minimum time schedule for this. And I've got them here in the book. I hope I did this. I hope I got the same thing figured out here. Okay, so let's. Can you zoom up a little closer on this? Great. Okay, even closer. More, yeah. So okay. Now here I put question mark because that's somebody up in the future here that it's going to be. You know, I'll know what that is, but I have to read in one of these future blocks. The point is that by the time I'm able to look at block D5 at time 9 here, you see there's a lot of congestion on this. So by the time of D9, I have to have read D6, and all of these question mark, there's 15 guys, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 guys from the future after D5. Because of this congestion, this guy D5 wasn't ready until time 9, and still I've got. If you look at this, I'm still sitting here. I have a buffer that has a bunch of stuff from A3. I've got a buffer with a bunch of stuff from B2 and C1 and E4 and F3 and G2 and B1. And so by the time I'm able to look at D5, I've got to have these 15 bufferfuls of stuff that are way in the future. There was, I needed them in order to keep the disk going while waiting for D5. So I'm sitting here with 16 plus 8 plus 5 input records in memory before I'm able to use it. Well, if you work out the worst case, it turns out that if you're doing a p-way merge on D disks, and then you need approximately 1/2 PD buffers. The actual formula, it's one of these. The actual formula is one of these victories for concrete mathematics. It's one of the things that we one of the problems that's solved in the book Concrete Mathematics. The actual formula of the number of buffers that is necessary and sufficient is 1/2 PD plus 3/2 D plus 1/2 P plus half the greatest common divisor of P and D minus 1. And it turns out that if you have that many buffers, and if you stripe them so that the J file goes on, you use here the ceiling of JD over P. You take, the first one goes on to, anyway, you take this number, and this sequence goes from 0 up to D minus 1 as J goes from 1 to P. And so you put the first block of each file in this way, then you can make sure that by the combinatorics of it, that you'll never need more than about 1/2 PD buffers. And the superblock striping method would mean P times D buffers, because each of your P input records you're using D buffers for them. So you can get by with this method with half as many buffers. But I haven't got. But there's a better way yet, and the better way, number of buffers is in the order of P plus D log D buffers to get almost as good as perfect. So this gives you the optimum, absolute best possible time. If you have this many buffers, you can make sure that the disks are always going, and you don't run out of buffer space because you're guaranteed to have. Because of the striping, you're guaranteed that the worst case can't get worse than that. But there's a better way where you only need a lot fewer buffers when P and D are large, where you can get almost that speed within a few percent. And that's the randomized striping technique, which I want to show you. It's also very simple. Okay, put my pages back here. But someday you have to buy Volume 3, the new edition, and learn how you do that. Now, okay, so let me give you the same example, the same chronological order for the 8-way merge, but I'm going to put these files in randomly now instead of A on disk 0, B on disk 1, and C starting on disk 2, and so on. I'm going to randomly stripe them. So I used offsets, x1 for first file, x2 for the second file, and I took pi as an example. It's my first idea when I have to give an example with random numbers. I always use digits of pi, and 3, 1, 4, 1, 5, 9. Well, here I've taken mod 5, so offset is 0 instead of 5 instead of 9. But this is based on pi, and so the same example that we had there, I would then put A0 here and B0 there, and at the beginning it's not a win, because at the beginning I have a little more congestion before I can start the merge. I had to get all the way up to the H here. Before I got all 8 blocks written, it took me 3 cycles to read instead of 2. But in general, these numbers are chosen at random, and they're different every time you run the. Every time you have to write a file onto disk, you choose a random number once and for all for that file, and then you stripe cyclically from that point on. And that's the whole idea of randomized striping, is that you use this one time for each file. You generate a random offset for it, and then you proceed cyclically, A1, A2, A3, and 4. You don't generate random numbers for every block, just for the starting block. And it's going to turn out that if we do this, we have a very small chance of getting a bad case. The worst case can still be bad, can still be this 1/2 PD, buffers if you wanted to go at full speed. But the probability of getting that case is so small that it just isn't going to happen. So this is the idea of randomized striping, and I want to give credit that this appeared in the journal Parallel Computing this year, and it's by Russ. What's his name? I forget his first name. This is Eddie Grove. Some people might have known Eddie Grove. He was a student at Berkeley and years ago, and Jeff Vitter at Duke University. And this is the idea of randomized striping that they were the first to analyze. And I made a little improvement on their analysis, but not much. The main ideas are theirs. My idea was to change the parameters a little bit in their scheme. When I say Q, they took Q equals P. And so all I did was take what's in their paper, and I generalized it to realize that it's more flexible if you have an extra parameter, P and Q, these are the input buffers that we're going to be dealing with. So D is the number of disks, P is the order of merge, and Q is an extra parameter that says how many scratch buffers I'm going to have. They took Q equal to P, but you can choose Q to be for example, D log D or something like that. Anything you can choose Q to be 0, but the method depends on the bigger Q is, the more buffers you have, and you get a little bit faster speed. And so here's the idea is I'm going to illustrate it with this particular pattern of reading in the same chronological order as before, and the idea is that I have 3 kinds of buffers, and each buffer changes its status at different times. But there's active reading buffers, and there's always going to be D of those. And then there's active merging buffers, from which I'm getting input, and there's P of these. So I'm doing a P-way merge, like 8-way merge, and I got 5 disks, say. And so at a given time, I've got P buffers from which I'm getting input, and D buffers on which input is happening right then. I can't look at those buffers. The operating system has locked those out, but the reading is going on into those buffers during this cycle. And then I've got scratch buffers, and there's D minus 1 plus Q. I've got at least D minus 1 scratch buffers, because as soon as the reading is done, as soon as the reading is done, my computer is fast enough that one of these merge buffers is going to have emptied, and I can immediately use that for the next read, and then I got to get D minus 1 scratch buffers to keep the other disk busy. So D is 5, then I need at least 4 scratch buffers because I'm reading from each disk, and at the end of that read, one of those disks, one of my input buffers is free, and then I'm going to get 4 scratch buffers, and I can start again immediately to read the next 5 blocks, one on each disk. So these are, and so Q is this parameter that can start at 0 and go up. And I'm going to consider, in my example, D is 5, P is 8, and Q is 4. So Q is 4, and so this is 8 altogether here. And I'm going to just watch this as time goes on. So time 1, we are going to be actively reading E0, B0, G0, A0, C0, meaning from disk 0 I'm reading this first block, and from disk 1 I'm reading the first block on each disk. Okay, and I'm also going to write. Let's see, we got room here on the screen, I hope. So here I'm going to say. Well, let me just put in this column the guy that I'm waiting for a certain one, and at the first step, I'm waiting for A0. It means the thing I'm waiting for is the first block in chronological order that hasn't entered the merge yet. So at the beginning, I'm waiting for the very first block in chronological order, which was A0. Remember, this was the chronological order. This long string here is the chronological order. So I'm waiting for A0, and these merge buffers are all sitting here empty. At the beginning, the scratch buffers are all empty. Now at time 2, then I'm going to be waiting for D0. The reason is, you see, at the end of the read, A0 is going to be in there, and B0 is going to be in there, and C0 is going to be in there, but D0 wasn't one of the guys that I got in my read. So I'm waiting. So the first guy in chronological order that hasn't been read in yet is D0. Okay. So at time 2, what are we picking up? On the first one, we must be reading F1 on the first disk. The second disk, we must be reading D0. The third disk, we must be reading D1. Disk 3, we must be reading D2. And here we must be reading F0 according to chronological order. So on each disk, we read. We got this nice prefetching foreknowledge, so we know which disk to read from at each time. And I'm waiting for D0, but the one I'm waiting for is always going to be one of these it's always going to be first on this disk, because everything previously on this disk we've already read in. We always read in the chronological order, which we're able to predict from looking at this extra small files. Okay, so the at this time, actually, active merging. I don't know why I put B0 and C0 in there. I shouldn't have done. I'm sorry. I want to be systematic. So I'm going to put B0. I'm not going to put into any active merging anything after the one I was waiting for, and so B0 and C0 were later. Okay, now, but I've also got E0, G0. I'm going to explain this notation in a minute, but in my scratch buffers at time 2, I've got this extra information I read ahead, B0, C0, E0, G0, which came in at time 1, and I know that D0 is the first guy that I'm waiting for. And in my active merging, I'm going to put everything up to the one I was waiting for before. So these are all blank yet. I haven't got very much active merging work going yet. But then in parenthesis is people that are read in that were after the one I'm waiting for now. So E and G are there, but they follow D, the guy that I was waiting for now. The reason for distinguishing between these is that I'm assuming my computer is fast compared to the disk. So I'm assuming that although I'm waiting for D0, I'm going to get to B0 and C0 into the active merging process before the read is complete. So at time 3, the A0 and B0 and C0 and D0 are going to be ready. The computer caught up with this, and I was waiting for D0, and so as soon as that's done, this guy is active. Then in my scratch buffers, in chronological order, I'm sitting with E0, F0, G0, D1, D2, and F1 in chronological order. But now who am I waiting for? The first guy I'm waiting for is H0. I've got G0 in here, F0 is in here, everything is, so H0 is the guy I'm waiting for now. So anybody following H0 in this chronological order has to go in parentheses here. I'll explain the parentheses a little more, but that's my convention, that anything before H0 is going to be considered, it's in the scratch buffer, but it's going to soon move to the active merge buffer. And then I'm reading the next things. So I'm reading A2 on this one. I'm reading on this one. I'm reading H0. On the third disk, I'm reading E2, B1. What? No, the third one, G1. G1 I'm reading here, and on the last disk I'm reading D3. It's a little hard to write out these charts, but the actual logic is fairly simple. I'm trying to give you the play-by-play to make you see why it's fairly simple. So I'm waiting on the first guy that I haven't been able to merge. So now what's going to happen is during the time this reading is going on, these three buffers are going to get over here into the active merge, and H0 is going to snap into active merging as well. And so that's going to be absorbed at the next time. E0, F0, G0. I'm actually getting the whole process initialized, taking a little time. And then who's going to be the next guy I'm waiting on? Well, it's the first one in chronological order that I haven't read in yet. So after H0, D1 is next, but I've got him in memory. E1, nope, haven't read E1 yet. So E1 is the one I'm going to be waiting on next. And in my buffers, I have D1, D2, E2, D3, F1, G1, and A2 from the future, and D1 occurred before the E1, but the others occurred after. Now I get to tell you the new rule, and that is where Q comes in. I'm only going to be, of the guys in parentheses, only Q of these are going to survive. I only have enough room for Q. I have to have 4, let's see, 1, 2, 3, 4, 5, 6, 7. There's actually a blank here. But I need 4 buffers to start for the disk at time 5. So I'm going to have to actually forget that I read these guys, because D1 will be clear at the time I have to do the next read, and this guy is still clear. But these two, but I'm going to need 4 extras. The Q is 4, so it says that all the guys in parentheses, you can only keep Q of them. This is how much you can look ahead of the guy that you're waiting for. And so if Q is 0, I would have had to cross these guys out earlier. So G1 and G and what was that? And A2, I have to read them again. So at time 4, I actually reread these guys. But then I go on the other disks. I go on and move with progress on those disks. Okay, so that is the. I'll go to time 5, and then you'll get the idea. So it's going to be E1 and B1 on this one, but I'm rereading the same guy. In some cases, it turned out you might even have to back up and go back and read one that you not only reread one that you just read, but read one that you had read before, because all of a sudden you ran out of buffers. It gets surprising, but it can happen, and that's exercise 25. Now what I've done, however, is kept the disk going at pretty much full speed. I've only had to back up. I've only had to lose 2 ticks over maximum speed in this particular example. And we'll do time 5, and then I'll go on to explain the theory. which the basis of the theory anyway. So now who am I waiting for after E1? I'll have all of these guys in memory, and well, it turns out F2 is the one. I'll have D3, I'll have A1, F1, B1, G1, A2 will all be there, but F2 has not occurred yet. And so at time 5, the actual details is that I'm reading D4, F3, H3, E3, G2. This is just for the people who are watching it on videotape. They can check that I did this right. And if there's an error, by the way, you can tell me, and if you're the first to tell me, you win $2.56 after volume 3. Even before volume 3 comes out, you can get credit for this error. And the next step would be D2, E2, D3, A1, F1, B1, G1, A2, and nothing in parentheses. As it turns out that at this point, all of these guys in scratch buffers are going to be usable before I need to get to time 6. And, well, anyway, the algorithm goes on like this. And every once in a while you might have to reread something, but you know, there's possible hang-ups. Well, now that the theory, I'm not going to give the proof, but I want to explain how they do it. The theory says that no matter what chronological sequence you have, the chances of a bad case are very low, and I can quantify it. But that's the general idea of a randomized algorithm. That is, no matter which order the sequence. There's a simple kind of randomized algorithm that says if this order were random, then we would do okay. But there's another case that if this order is decided in advance by the devil, but I can still do it with high probability because I've chosen these offsets at random. And the devil didn't know what my choices of the offsets was going to be. You have to take this on faith. But the universe is not deterministic. I did not. I had free will to choose these random offsets, and so therefore the chance of bad case is going to be very small. And the reason is like this: if we take any set of q plus 2 numbers in the chronological order. So, like in this case, six consecutive things out of the chronological order might have been D2, E2, D3, A1, F1. That's 5. I got to get the next guy, B1, whatever. So these are some pattern of 6 guys out of this chronological order, and I'm going to prove that. I'm going to see how much conflict can there be. How many disk cycles is it going to take to get through these q plus 2 things? And the argument is something like this. Well, I know that D2 and D3 are on different disks, but the other, because they both happen to be in the D file, and I did this striping. But the A, the B, the E, and the F they came from different files. So now the actual disks in which these things appear are sort of are random, and you imagine that we had. In probability theory, statisticians like to talk about balls in urns. And so we have D urns, you know, jars. And we throw 6 balls into these urns. And I'm going to throw in the ball, A1 went into a random one of these urns based on its offset. So it might have gone onto this disk. B1 went into some disk. Shows at random. You know, 5 has some way of generating a random number between 0 and 5. But these particular set of q plus 2 things I'm trying to figure out how much time they could contribute to the whole, to the entire process. And so it might have gone into a different one, might have gone in the same one. The D2 and D3, they went into two consecutive ones. The first, D2 was random, but D3 was undetermined by it. And the E went into a random one, and F went into a random one. Now, so consider this statistical problem. You're throwing in some number of balls into a certain number of urns, and you want to know what's the size, how many are going to be in the fullest urn, the one that has more balls. If all the balls, so here a case where we had two balls in this, well, it had to be some urn with two balls in it. But maybe in the worst case, I would have had 5 balls in the same urn. And that would have been bad news for this part of the chronological order. Okay, but for each part of the chronological order, the expected size of the fullest urn is going to govern be an upper bound on the time I need to get through this part of the process. And so now by using statistics of this balls in urns, burns in all. Of this classical occupancy problem from statistics, we can say that it's very unlikely that we're going to have a large number of balls in any urn, and so then we get from this we get the theory, and it turns out that the actual upper bounds that we get on the performance of randomized striping is given by this table I have here, which says it's a function of 2 parameters, and I illustrated for up to 1024 disks, and then the parameter you use is R of D and Q plus 2, and this gives so that if Q is 0, for example, this would say 1.5. This is the amount of time per cycle. So what you do is this is a multiplicative factor on the optimum time. You're never worse than this. Like if this says 2, if this says 1.7 here, you're never more than 1.7 times the absolute minimum time when you use randomized striping. This is an extremely conservative argument. In fact, simulations indicate that you really get more like 1.0, 0.05 or something like this. This is the upper bound that's so far been proved, and I expect the theory will be improved in the future to give a tighter upper bound. Right now, this is what we have, time is running short, but I want to show you just a couple of things quick before we quit. And one is this balls and urns problem is kind of there's a very tantalizing conjecture which I was not able to prove except to see that it was tantalizing, and so I sent it to a lot of mathematicians to popularize it. Here's an example where I'm saying, suppose we have 10 urns, and I put in 8 balls at each ball at random. So that's 1, 1, 1, 1, 1. It means that they're all from different files. And then the expected number of balls in the largest urn, if you throw in 8 balls at random into 10 urns, is 2.399. On the other hand, if you say that you've got 2 of those balls belong to the same file, so that means that you're going to put them into adjacent urns in this cyclic order, then the expected value drops down, and if you have 2, 2, and so on. So like this number here for 311 means that I'm getting 3 things out of one file and the others from different files. Here I'm saying I'm getting 2 things out of one, 2 things out of one. So this is a problem of balls and urns that you say you choose a random number for each of these. Like here I'm throwing choosing 5 random numbers, but the first random number I throw in 2 balls into 2 consecutive urns, and the second random number I throw in 2, then I throw in 2, then I throw in 1, and I throw in 1. And I say how many balls in the fullest urn, and it's getting smaller. And it stands to reason it has to get smaller because we know that when we're putting things into consecutive urns, we're somehow not putting them in the same urn. And so why should it pile up? So I made a stronger conjecture, that is that if you choose for each file not only its offset, but you also choose a pattern in which you're going to put the two balls. Like you're going to put in this file, you're going to put them next to each other. In the next file, you put them at positions 1, and then you skip 2, and then you put another one. And you have a different pattern of choice of patterns. You know they're going to be in different urns, but it's a different pattern in each case. Then it turned out not to be monotonic. I found a counterexample where you could actually rig these patterns in such a way that it was actually better to put them in independently instead of putting them in some stupid pattern. So it remains as a conjecture that by combining two of these numbers and replacing them by their sum, do you lower the expected value? That's an interesting mathematical problem. But actually, I believe that this theory is considerably less than the actual performance. For example, in the case Q equals 0, the ratio that you get according to the theory, this R of D and 2, turns out to be D plus 1 over 2, the number of disks, half the number of disks essentially. But I could analyze the process exactly in that case, and it turned out that the actual number was proportional to the square root of D. So it was something like square root of pi D over 8. I mean, but it was the number of in n units of time you can get through square root of D times n blocks. Even when you had Q equals 0, the smallest case in this randomized striping, while the theory, the upper bound said you needed half of D. So it's clear that there's a great difference between the upper bound we can prove now and the actual performance. Even so, the upper bound that we can prove now is good enough to show that if you take something like 5D log D buffers, then you can be within 5% of the optimum, 1.05. And so even with our weak theory, we know that this method is asymptotically very good. In practice, if you the simulations look extremely good. That all you have to do is every time is stripe the disks of the blocks of your file, but choose the starting file at random, and then go cyclically from there. And that looks like a very good way to avoid conflicts when you're doing highway merging. Okay, that's what I had to say today. Any urgent questions? We can maybe get them while the TV camera is still running. Yeah.
When you say log, is that log base 2?
I'm saying proportion. I meant log base 2, but if you don't know what the base is, then there is. If I want to get within epsilon, if I want my ratio to be 1 plus epsilon, then I just have to take something like, I don't know if it's 1 over epsilon d log d or something like that. But it's something that grows. If it's even if you're at a fairly small multiple of d log d, we can guarantee that epsilon is pretty good. Engineering-wise, it's solved. The actual formulas are kind of hairy looking, but actually the math wasn't that bad to get it. What? Okay, now VSAM was a method that uses that uses B trees and I mean it's got a different it's quite a different policy entirely. This is using full. Okay, these files are not intended. I'm considering that I'm building these blocks and packing them fully. I'm not doing insertions and deletions on the file as I'm doing it. So it's not a comparable question. Yeah. Okay. Okay. Thanks a lot.